So our goal now is to calculate the density of copper metal. Copper crystallizes in a face-centered cubic lattice. And so to calculate the density, we will need to find the mass of the unit cell and divide by the volume. Divide by the volume of the unit cell. Okay, so to find the mass of the unit cell, we know that in a face-centered cubic lattice that there are 4 atoms of copper inside the unit cell. We know that the mass of a mole of copper is 63.55 grams per mole. That's just the atomic weight of copper. And so we know that there's 4 atoms, but here we have grams per mole. So we need to figure out what is the mass of just 4 atoms of copper. And so to convert between those, we're going to use Avogadro's number. 10 to the 23rd atoms per mole. Okay, and if we do that, we work out that in one unit cell, there are 4.22 times 10 to the negative 22 grams of copper. So now we know the mass of copper inside the unit cell. We're next going to need the volume of the unit cell. So we know that the volume of a cube is going to be the edge length, A, cubed. And so how do we find the edge length of the cube? Well, if we think about a face-centered cube, if we just think about one of the faces, the atoms on the corners, they don't actually touch. But the atoms on the diagonal, they do. Here, let me adjust a little bit to show that, so that the atoms in the middle, they touch each other. Okay, so the face diagonal of a face-centered cube is 4 times the radius. So 4r here. We can find that length by using in the Pythagorean Theorem. So if we know the radius, we know that a squared plus a squared equals 4r quantity squared. And so if we solve for the radius or the lattice parameter in terms of the radius, so if we solve for a, the edge length, we will find that it is 2r times the square root of 2. So we come back over to our volume formula, and we know that the volume is going to be 2 times the radius of copper times the square root of 2 quantity cubed. So the radius of copper is, if we look that up, is 128 picometers. Now, a picometer is a great unit for an atomic radius, but it's crappy for density. Instead, we want our volume, our density, to come out in grams per cubic centimeter, so we need to convert our edge length to centimeters as well, so that we can get our volume in cubic centimeters. So if our radius is 128 picometers, then we know that there are 10 to the minus 12 meters in a picometer, and that there are 10 to the minus second meters in a centimeter. And so we can convert that 128 picometers is 1.28 times 10 to the 8th centimeters. If we put that into our volume formula, we get 2 times the radius in centimeters, so 1.28 times 10 to the minus 8 centimeters times the square root of 2. And then that whole thing is cubed. So calculator, and I get that the volume is 4.75 times 10 to the minus 23rd cubic centimeters. Now to go back to finding density, we're going to put the mass over the volume. So the mass we found was 4.22 times 10 to the minus 22nd grams of copper per unit cell, and that the volume of the unit cell was 4.75 times 10 to the minus 23rd cubic centimeters. So that means that the calculated density based on the atomic radius of copper is 8.89 grams per cubic centimeter. And so if we compare that to the experimental value, we see that the experimental value is 8.96 grams per cubic centimeter, which really is a pretty close match. So we can see that this is an effective way for calculating the density of a metal. It matches better in some cases than others when we think about like the difference between covalent and ionic bonding and how close those atoms are actually able to get to each other. But this approximation of these atoms being hard billiard balls and the copper atoms lining up in this way is pretty good. We could also imagine doing this for a different kind of unit cell, but we're going to have to figure out how to calculate the volume. So on the accompanying slide here, we have the lattice parameters, the edge lengths, in terms of the radius for the different unit cells. We could also imagine taking this backwards, where I give you the density and you have to back out the radius. So use this example as kind of a prototype, and let's think through some other examples for how we could use this information.